Chapter 7, Correlation. In several of the previous chapters, we have examined statistics and parameters that describe a single variable at a time, such as the mean, standard deviation, z-scores, and standard errors. Although such single variable statistics are important, researchers are often interested in examining the relations among two or more variables. One of the most basic measures of the association among variables, and a foundational statistic for several more complex statistics, is the correlation coefficient. Although there are a number of different types of correlation coefficients, the most commonly used in social science research is the Pearson product moment correlation coefficient. Most of this chapter is devoted to understanding this statistic, with a brief description of three other types of correlations: the point biserial coefficient, the Spearman-Rho coefficient, and the phi coefficient. When to use correlation and what it tells us. Researchers compute correlation coefficients when they want to know how two variables are related to each other. For a Pearson product moment correlation, both of the variables must be measured on an interval or ratio scale, otherwise known as continuous variables. So a normal curve only shows a single variable, such as a number of scores, in terms of the frequency in which they occur in a sample or population. For example, like the scores of students on a test. For example, suppose I wanted to know whether there was a relationship between the amount of time students spend studying for an exam and their scores on the exam. I suspect that the more hours students spend studying, the higher their scores will be on the exam. But I also suspect that there is not a perfect correspondence between time spent studying and test scores. Some students will probably get low scores on the exam even if they study for a long time, simply because they may have a hard time understanding the material. Indeed, there will probably be a number of students who spend an inordinately long time studying for the test precisely because they are having trouble understanding the material. On the other hand, there will probably be some students who do very well on the test without spending very much time studying. Despite these exceptions to my rule, I will still hypothesize that, on average, as the amount of time spent studying increases, so do students' scores on the exam. There are two fundamental characteristics of correlation coefficients researchers care about. The first of these is the direction of the correlation coefficient. Correlation coefficients can be either positive or negative. A positive correlation indicates that the values on the two variables being analyzed move in the same direction. That is, as scores on one variable go up, scores on the other variable go up as well, on average. Similarly, on average, as scores on one variable go down, scores on the other variable go down. Returning to my earlier example, if there is a positive correlation between the amount of time students spend studying and their test scores, I can tell that, on average, the more time students spend studying, the higher their scores on the test. This is equivalent to saying that, on average, the less time they spend studying, the lower their scores on the test. Both of these represent a positive correlation between time spent studying and test scores. Note, I keep saying on average, because it is important to note that the presence of a correlation between two variables does not mean that this relationship holds true for each member of the sample or population. Rather, it means that, in general, there is a relationship of a given direction and strength between two variables in the sample or population. A negative correlation indicates that the values of the two variables being analyzed move in opposite directions. That is, as scores on one variable go up, scores on the other variable go down, and vice versa, on average. If there were a negative correlation between the amount of time spent studying and test scores, I would know that, on average, the more time students spend studying for the exam, the lower they actually score on the exam. Similarly, with a negative correlation, I would also conclude that, on average, the less time students spend studying, the higher their scores on the exam. These positive and negative correlations are represented by scattergrams in Figure 7.1. Scattergrams are simply graphs that indicate the scores of each case in a sample simultaneously on two variables. For example, in the positive correlation scatter graph in Figure 7.1, the first case in the sample studied for 1 hour and got a score of 30 on the exam. The second case studied for 2 hours and scored a 40 on the exam. Figure 7.1 is a scatter plot showing examples of positive and negative correlations. So In the graph on the left, there's a positive correlation, and you can see as the hours spent studying on the x-axis, numbers go up. The score on the exam numbers on the y-axis also go up. Then on the right, there's a negative correlation. As students study for more hours, the number of hours on the x-axis goes up. The score on the exam, the numbers on the y-axis, go down. The second fundamental characteristic of correlation coefficients is the strength or magnitude of the relationship. Correlation coefficients range in strength from negative 1.00 or positive 1.00. A correlation coefficient of 0.00 indicates that there is no relationship between the two variables being examined. That is, scores on one of the variables are not related in any meaningful way to scores on the second variable. The closer the correlation coefficient is to either negative 1.00 or positive 1.00, the stronger the relationship is between the two variables. A perfect negative correlation of negative 1.00 indicates that for every member of the sample or population, a higher score on one variable is related to a lower score on the other variable. A perfect positive correlation of positive 1.00 reveals that for every member of the sample or population, a higher score on one variable is related to a higher score on the other variable. Perfect correlations are never found in actual social science research. Generally, correlation coefficients stay between negative 0.70 and positive 0.70. Some textbook authors suggest that correlation coefficients between negative 0.20 and positive 0.20 indicate a weak relationship between two variables. Those between 0.20 and 0.50, either positive or negative, represent a moderate relationship, and those larger than 0.50, either positive or negative, represent a strong relationship. These general rules of thumb for judging the relevance of correlation coefficients must be taken with a grain of salt. For example, even a small correlation between alcohol consumption and liver disease, for example, positive 0.15, is important, whereas a strong correlation between how much children like vanilla and chocolate ice cream, for example, positive 0.70, may not be so important. The scatter plots presented in Figure 1 represent very strong positive and negative correlations, R equals 0.97 and R equals negative 0.97 for the positive and negative correlations, respectively. R is the symbol for the sample Pearson correlation coefficient. In Figure 7.2, a scatter plot representing virtually no correlation between the number of hours spent studying and the scores on the exam is presented. Notice that there is no discernible pattern between the scores on the two variables. In other words, the data presented in Figure 7.2 revealed that it would be virtually impossible to predict an individual's test score simply by knowing how many hours the person studied for the exam. Figure 7.2. No correlation between hours spent studying and exam scores. So the hours spent studying is on the x-axis between 0 to 12 hours, and the scores on the exam are on the y-axis from 0 to 100, and you can see the data points are just like a cloud of data points. There's no pattern. Pearson correlation coefficients in depth. The first step to understanding how Pearson correlation coefficients are calculated is to notice that we are concerned with a sample scores on two variables at the same time. Returning to our previous example of study time and test scores, suppose that we randomly select a sample of 5 students and measure the time they spend studying for the exam and their exam scores. The data are presented in Table 7.1. Table 7.1, data for correlation coefficient. So student 1 spent 5 hours studying and got an exam score of 80. Student 2 spent 6 hours studying and got an exam score of 85. Student 3 spent 7 hours studying and got an exam score of 70. Student 4 spent 8 hours studying and got an exam score of 90. Student 5 spent 9 hours studying and got an exam score of 85. For these data to be used in a correlation analysis, it is critical that the scores on the two variables are paired. That is, for each student in my sample, the score on the x variable, hours spent studying, is paired with his or her own score on the y variable, exam score. If I want to determine the relation between hours spent studying and exam scores, I cannot pair student 1's hours spent studying with student 4's test score. I must match each student's score on the x variable with his or her own score on the y variable. Once I have done this, I can determine whether, on average, hours spent studying is related to exam scores. Calculating the correlation coefficient. There are several different formulas that can be used to calculate Pearson product moment correlation coefficients. Each of these formulas produces the same result and differ only in their ease of use. In fact, none of them are particularly easy to use. I present one of them here to illustrate the principles of correlation coefficients. Should you find yourself in need of knowing the relation between two variables, I recommend that you use a calculator or a statistics program that generates correlation coefficients for you. The formula presented in Table 7.2 requires that you standardize your variables. See Chapter 4. Remember that when you standardize a variable, you are simply subtracting the mean from each score in your sample and dividing by the standard deviation. What this does is provide a z-score for each case in the sample. Those members of the sample with scores below the mean will have negative z-scores, whereas those members of the sample with scores above the mean will have positive z-scores. And the z-score shows z-scores are in standard deviation units, so they show how many standard deviations above or below the mean the score is. And if it's positive, it's above the mean. If it's a negative score, it's below the mean. So a z-score of 3 would mean you're 3 standard deviations above the mean. Table 7.2, definitional formula for Pearson correlation. R equals the sum of zx times zy all over n, where R equals the Pearson product moment correlation coefficient, Zx equals a z-score for a variable x, Zy equals a paired z-score for variable y, n equals the number of pairs of x and y scores. Notice that this formula looks similar to some of the other formulas that we have already encountered. For example, the denominator is n, which is the number of pairs of scores. For example, the number of cases in the sample. Whenever we divide by n, we are finding an average. This was true when we examined the formula for the mean in Chapter 1 and the formulas for variance and standard deviation in Chapter 2. So we know that the correlation coefficient will be an average of some kind. But what is it an average of? Now take a look at the numerator. Here, we see that we must find the sum of something. Recall that when discussing the formulas for the variance and standard deviation in Chapter 2, we also encountered the summation sign in the numerator. There, we had to find the sum of the squared deviations between each individual score and the mean, but in the formula for computing the correlation coefficient, we have to find the sum of the cross products between the z-scores on each of the two variables being examined for each case in the sample. When we multiply each individual's score on one variable with that individual score on the second variable, for example, find a cross product, sum those across all of the individuals in the sample, and then divide by n, we have an average cross product, and this is known as covariance. If we standardize this covariance, we end up with a correlation coefficient. In the formula provided in Table 7.2, we simply standardized the variables before we computed the cross products, thereby producing a standardized covariance statistic, which is a correlation coefficient. In this formula, notice what is happening. First, we are multiplying the paired z-scores together. When we do this, notice that if an individual case in the sample has scores above the mean on each of the two variables being examined, the two z-scores being multiplied will both be positive, and the resulting cross product will also be positive. Similarly, if an individual case has scores below the mean on each of the two variables, the two z-scores being multiplied will both be negative, and the cross product will again be positive. Therefore, if we have a sample where low scores on one variable tend to be associated with low scores on the other variable, and high scores on one variable tend to be associated with high scores on the second variable, then when we add up the products from our multiplications, we will end up with a positive number. This is how we get a positive correlation coefficient. Now consider what happens when high scores on one variable are associated with low scores on the second variable. If an individual case in a sample has a score that is higher than the average on the first variable, i.e. a positive z-score, and a score that is below the mean on the second variable, i.e. a negative z-score, when these two scores are multiplied together, they will produce a negative product. If, for most of the cases in the sample, high scores on one variable are associated with low scores on the second variable, the sum of the products of the z-scores, the sum of zx, zy, will be negative. This is how we get a negative correlation coefficient. What the correlation coefficient does and does not tell us. Correlation coefficients, such as the Pearson, are very powerful statistics. They allow us to determine whether, on average, the values on one variable are associated with the values on a second variable. This can be very useful information, but people, including social scientists, are often tempted to ascribe more meaning to correlation coefficients than they deserve. Namely, people often confuse the concept of correlation and causation. Correlation, correlation, simply means that variation in the scores on one variable correspond with variation in the scores on a second variable. Causation means that variation in the scores on one variable cause or create variation in the scores on a second variable. When we make the leap from correlation to causation, we may be wrong. As an example, I offer this story, which I heard in my introductory psychology class. As the story goes, one winter shortly after World War II, there was an explosion in the number of storks nesting in some northern European country, I cannot remember which. Approximately 9 months later, there was a large jump in the number of babies that were born. Now, the link between storks and babies being what it is, many concluded that this correlation between the number of storks and the number of babies represented a causal relationship. Fortunately, science tells us that babies do not come from storks after all, at least not human babies. However, there is something that storks and babies have in common. Both can be summoned by cold temperatures and warm fireplaces. It seems that storks like to nest in warm chimneys during cold winters. As it happens, cold winter nights also foster baby-making behavior. The apparent cause and effect relationship between storks and babies was in fact caused by a third variable, a cold winter. For a more serious example, we can look at the relationship between SAT scores and first-year college grade point average. The correlation between these two variables is about 0.40. Although these two variables are moderately correlated, it would be difficult to argue that higher SAT scores cause higher achievement in the first year of college. Rather, there is probably some other variable or set of variables responsible for this relationship. For example, we know that taking a greater number of advanced math courses in high school is associated with higher SAT scores and with higher grades in first-year math courses in college. The point of these examples is simple. Evidence of a relationship between variables, i.e. a correlation, does not necessarily mean that there is a causal relationship between the two variables. However, it should also be noted that a correlation between two variables is a necessary ingredient of any argument that the two variables are causally related. In other words, I cannot claim that one variable causes another, i.e. that smoking causes cancer, if there is no correlation between smoking and cancer. If I do find a correlation between smoking and cancer, I must rule out other factors before I can conclude that it is smoking that causes cancer. In addition to the correlation-causation issue, there are a few other important features of correlations worth noting. First, simple Pearson correlations are designed to examine linear relations among variables. In other words, they describe average straight relations among variables. For example, if you find a positive correlation between two variables, you can predict how much the scores in one variable will increase with each corresponding increase in the second variable. But not all relations between variables are linear. For example, there is a curvilinear relationship between anxiety and performance on a number of academic and non-academic behaviors. When taking a math test, for example, a little bit of anxiety actually may help performance. However, once a student becomes too nervous, this anxiety can interfere with performance. We call this a curvilinear relationship because what began as a positive relationship between performance and anxiety at lower levels of anxiety becomes a negative relationship at higher levels of anxiety. This curvilinear relationship is presented graphically in Figure 7.3. Because correlation coefficients show the average relation between two variables, when the relationship between two variables is curvilinear, the correlation coefficient can be quite small, suggesting a weaker relationship than may actually exist. Table 7.3, data for studying exam score correlation. So student 1 spent 0 hours studying and got an exam score of 95. Student 2 spent 2 hours studying and got an exam score of 95. Student 3 spent 4 hours studying and got an exam score of 100. Student 4 spent 7 hours studying and got an exam score of 95. Student 5 spent 10 hours studying and got an exam score of 100. Another common problem that arises when examining correlation coefficients is the problem of truncated range. This problem is encountered when the scores on one or both of the variables in the analysis do not have much variety in the distribution of scores, possibly due to a ceiling or floor effect. For example, suppose that I gave a sample of students a very easy test with a possible high score of 100. Then suppose I wanted to see if there was a correlation between scores on my test and how much time students spent studying for the test. Suppose I got the following data presented in Table 7.3. Figure 7.3, a curvilinear relationship. So on the x-axis you have anxiety from 1 to 5, and on the y-axis you have performance from 0 to 70. And you can see that there's an upward slope, and it's almost linear up to the midpoint of the anxiety curve at 3, and then showing the performance goes up as anxiety goes up, and then after the midpoint at 3, as anxiety goes up, performance goes down. In this example, all of my students did well on the test, whether they spent many hours studying for it or not. Because the test was too easy, a ceiling effect may have occurred, thereby truncating the range of scores on the exam. Although there may be a relationship between how much time students spend studying and their knowledge of the material, my test was not sensitive enough to reveal this relationship. The weak correlation that will be produced by the data in Table 7.3 may not reflect the true relationship between how much students study and how much they learn. Wrapping up and looking forward, correlation coefficients, in particular Pearson correlation coefficients, provide a way to determine both the direction and the strength of the relationship between two variables measured on a continuous scale. This index can provide evidence that two variables are related to each other or that they are not, but does not, in and of itself, demonstrate a causal association between two variables. In this chapter, we were also introduced to the concepts of explained or shared variance and the coefficient of determination. Determining how much variance in one variable is shared with or explained by another variable is at the core of all of the statistics that are discussed in the remaining chapters of this book. In particular, correlation coefficients are the precursors to the more sophisticated statistics involved in multiple regression. Glossary of terms and symbols for Chapter 7. Causation. The concept that variation in one variable causes variation in another variable. Coefficient of determination. A statistic found by squaring the Pearson correlation coefficient that reveals the percentage of variance explained in each of the two correlated variables by the other variable. Continuous variables. Variables that are measured using an interval or ratio scale. Correlation coefficient. A statistic that reveals the strength and direction of the relationship between two variables. Curvilinear, a relationship between two variables that is positive at some values but negative at other values. Degrees of freedom. Roughly the minimum amount of data needed to calculate a statistic. More practically, it is a number or numbers used to approximate the number of observations in the dataset for the purpose of determining statistical significance. Dichotomous variable, a categorical or nominal variable with two categories. Direction, a characteristic of a correlation that describes whether two variables are positively or negatively related to each other. Explained variance, the percentage of variance in one variable that we can account for or understand by knowing the value of the second variable in the correlation. Negative correlation, a descriptive feature of a correlation indicating that as scores on one of the correlated variables increase, scores on the other variable decrease, and vice versa. Pearson product moment correlation coefficient, a statistic indicating the strength and direction of the relation between two continuous variables. Perfect negative correlation, a correlation coefficient of R equals negative 1.0. When the increasing scores of a given size on one of the variables in a correlation are associated with decreasing scores of a related size on the second variable in the correlation. For example, for each 1 unit increase in the score on variable X, there is a corresponding 2-unit decrease in the scores on variable Y. Perfect positive correlation, a correlation coefficient of R equals positive 1.0. When the increasing scores of a given size on one of the variables in a correlation are associated with increasing scores of a related size on the second variable in the correlation. For example, for each 1 unit increase in the score on variable X, there is a corresponding 2-unit increase in the scores on variable Y. Positive correlation, a characteristic of a correlation is the direction. When the scores on the two correlated variables move in the same direction on average, as the scores on one variable rise, scores on the other variable rise, and vice versa. Raw score formula, a formula used to calculate a statistic using only raw scores. Shared variance, the concept of two variables overlapping such that some of the variance in each variable is shared. The stronger the correlation between two variables, the greater the amount of shared variance between them. Spearman-Rho coefficient, the correlation coefficient used to measure the association between two variables measured on an ordinal scale, i.e. ranked data. Strength, magnitude, a characteristic of the correlation with a focus on how strongly two variables are related. Truncated range, when the responses on a variable are clustered near the top or the bottom of the possible range of scores, thereby limiting the range of scores and possibly limiting the strength of the correlation. Z-score, standardized score. R, symbol for the sample Pearson correlation coefficient. Rho, symbol for rho, the population correlation coefficient. SR, symbol for the standard error of the correlation coefficient. R squared, symbol for the coefficient of determination. DF, symbol for degrees of freedom. Phi, symbol for the phi coefficient, which is a correlation between two dichotomous variables. The coefficient of determination. Although correlation coefficients give an idea of the strength of the relationship between two variables, they often feel a bit nebulous. If you get a correlation coefficient of 0.4, is that a strong relationship? Fortunately, correlation coefficients can be used to determine a more concrete feeling statistic, the coefficient of determination. Even better, it is easy to calculate. When we want to know if two variables are related to each other, we are really asking a somewhat more complex question. Are the variables in the scores on one variable somehow associated with the variations in the scores on a second variable? Put another way, a correlation coefficient tells us whether we can know anything about the scores on one variable if we already know the scores on a second variable. In common statistical vernacular, what we want to be able to do with a measure of association, like a correlation coefficient, is be able to explain some of the variance in the scores on one variable with the scores on a second variable. The coefficient of determination tells us how much of the variance in the scores of one variable can be understood or explained by the scores on a second variable. Figure 7.4, uncorrelated variables, R equals 0.00, R squared equals 0.00. One way to conceptualize explained variance is to understand that when two variables are correlated with each other, they share a certain percentage of their variance. Consider an example. If we have a sample of 10 people and we measure their height and their weight, we've got 10 scores on each of two variables. Assuming that my 10 people differ in how tall they are, there will be some total amount of variance in their scores on the height variable. There will also be some total amount of variance in their scores on the weight variable, assuming that they do not all weigh the same amount. These total variances are depicted in figure 7.4 as two full squares, each representing 100% of the variance in their respective variables. Notice how they do not overlap. When two variables are related or correlated with each other, there is a certain amount of shared variance between them. In figure 7.4, the two squares are not touching each other, suggesting that all of the variance in each variable is independent of the other variable. There is no overlap. But when two variables are correlated, there is some shared variance. The stronger the correlation, the greater the amount of shared variance. And the more variance you can explain in one variable by knowing the scores on the second variable. The precise percentage of shared or explained variance can be determined by squaring the correlation coefficient. This squared correlation coefficient is known as the coefficient of determination. Some examples of different coefficients of determination are presented in figure 7.5. The stronger the correlation, the greater the amount of shared variance, and the higher the coefficient of determination. It is still important to remember that even though the coefficient of determination is used to tell us how much of the variance in one variable can be explained by the variance in a second variable, coefficients of determination do not necessarily indicate a causal relationship between the two variables. Figure 7.5, examples of different coefficients of determination. So in the first picture, you can see the two squares are overlapping a bit, and the r is 0.30 and r squared is 0.09. In the second picture, they're overlapping more, the two squares, and you can see r equals 0.55 and r squared equals 0.30. A brief word on other types of correlation coefficients. Although Pearson correlation coefficients are probably the most commonly used and reported in the social sciences, they are limited by the requirement that both variables are measured on interval or ratio scales. They have to be quantitative. Fortunately, there are methods available for calculating the strength of the relationship between two variables, even if one or both variables are not measured using interval or ratio scales. In this section, I briefly describe three of these other correlation coefficients. It is important to note that all of these statistics are very similar to the Pearson correlation coefficient, and each produces a correlation coefficient that is similar to the Pearson R. They are simply specialized versions of the Pearson correlation coefficient. They can be used when one or both of the variables are not measured using interval or ratio scales. Point biserial. When one of our variables is a continuous variable, i.e. measured on an interval or ratio scale, and the other is a two-level categorical, aka nominal variable, also known as a dichotomous variable, we need to calculate a point biserial correlation coefficient. This coefficient is a specialized version of the Pearson correlation coefficient discussed earlier in this chapter. For example, suppose I wanted to know whether there was a relationship between whether a person owns a car, yes or no, and their score on a written test of traffic rule knowledge, such as the test one must pass to get a driver's license. In this example, we are examining the relationship between one categorical variable with two categories, whether one owns a car or not, and one continuous variable, one's score on the driver's test. Therefore, the point biserial correlation is the appropriate statistic in this instance. Phi. Sometimes researchers want to know whether two dichotomous variables are correlated. In this case, we would calculate a phi coefficient, which is another specialized version of the Pearson R. For example, suppose I wanted to know whether gender, male, female, was associated with whether one smokes cigarettes or not, smoker, non-smoker. In this case, with two dichotomous variables, I would calculate a phi coefficient. Note, those readers familiar with chi-square analysis will notice that two dichotomous variables can also be analyzed using chi-square. Spearman-Rowe. Sometimes data are recorded as ranks, because ranks are a form of ordinal data and the other correlation coefficients discussed so far involve either continuous, interval, ratio, or dichotomous variables. We need a different type of statistic to calculate the correlation between two variables that use ranked data. The Spearman-Rowe, a specialized form of the Pearson R, is appropriate. For example, many schools use students' grade point averages, a continuous scale, to rank students, an ordinal scale. In addition, students' scores on standardized achievement tests can be ranked. To see whether a student's rank in their school is related to their rank on the standardized test, a Spearman-Rho coefficient can be calculated. Example: the correlation between grades and test scores. Student achievement can be measured in a variety of ways. One common method of evaluating students is to assign them letter grades. These grades can be converted into numbers, for example, A equals 4, B equals 3, etc. In high school, student grades across all of their classes, for example, mathematics, science, social studies, etc., can be combined into an average, thereby creating a grade point average, GPA, which is measured on a continuous interval scale ranging from a possible low of 0 to a possible high of 4.33, if the school gives grades of A+. Because grades are assigned by teachers, they are sometimes considered to be overly subjective. That is, different teachers may assign different grades to the same work. Similarly, there are some individual teachers that may give different grades to two students who produce the same quality of work. To ostensibly overcome such subjectivity, another form of assessment, the standardized test, was created. With this type of assessment, all students of a given grade level answer the same questions, and their responses are scored by computer, thereby removing the human element and its subjectivity. Some argue that standardized tests of ability and teacher-assigned grades generally measure the same thing. That is, for the most part, bright students will score well both on the test and in their grades. Others argue that standardized tests of ability and teacher-assigned grades really measure somewhat different things. Whereas standardized tests may measure how well students answer multiple choice questions, teachers have the benefit of knowing students and can take things like students' effort, creativity, and motivation into account when assigning grades. The first step in discovering which of these two viewpoints is more accurate is to see how strongly grades and test scores are related to each other. If there is a very strong correlation between the two, then both grades and test scores may in fact be measuring the same general trait. But if the two scores are only moderately correlated, perhaps they really do measure separate constructs. By constructs, I mean the actual thing that we are trying to measure. In the preceding example, if grades and test scores are strongly correlated, we could argue that both of these measures represent some underlying construct, such as intelligence or academic ability. On the other hand, if these two variables are not strongly correlated, they each may represent different things or constructs. My colleague, Carol Giancarlo, and I recently collected data from a sample of 314 11th grade students at a high school in California. Among the data we collected were their cumulative GPA, i.e. their GPA accumulated from the time they began high school until the time the data were collected. In addition, we gave students the Naglieri nonverbal test of abilities, a nonverbal test of general mental reasoning and critical thinking skills. To see if there was a statistically significant correlation between these two measures of ability, I used the SPSS statistical software program to calculate a correlation coefficient and a p-value. The SPSS printout for this analysis is presented in Table 7.5. The results presented in Table 7.5 provide several pieces of information. First, there are 3 correlation coefficients presented. The correlations on the diagonal show the correlation between a single variable and itself. Therefore, the first correlation coefficient presented reveals that GPA is correlated with itself perfectly, R equals 1.0000, because we always get a correlation of 1.00 when we correlate a variable with itself. These correlations presented on the diagonal are meaningless. That is why there is not a p-value reported for them. The numbers in the parentheses, just below the correlation coefficients, report the sample size. There were 314 11th grade students in this sample. The correlation coefficient that is off the diagonal is the one we're interested in. Here, we can see that students' GPA was moderately correlated with their scores on the Naglieri test, R equals 0.4291. This correlation is statistically significant, with a p-value of less than 0.0001. P is less than 0.0001. Table 7.5, SPSS printout of correlation analysis. So you have the GPA and the Naglieri. So when you don't go on the diagonal, you see GPA and Naglieri are correlated by R equals 0.4291, N equals 3.314, and P equals 0.000. To gain a clearer understanding of the relationship between GPA and Naglieri test scores, we can calculate a coefficient of determination. We do this by squaring the correlation coefficient. When we square this correlation coefficient, 0.4291 times 0.4291 equals 0.1841. We see that GPA explains a little bit more than 18% of the variance in the Naglieri test scores. Although this is a substantial percentage, it still leaves more than 80% of the ability test scores unexplained. Because of this large percentage of unexplained variance, we must conclude that teacher-assigned grades reflect something substantially different from general mental reasoning abilities and critical thinking skills as measured by the Naglieri test. Wrapping up and looking forward again, correlation coefficients, in particular Pearson correlation coefficients, provide a way to determine both the direction and the strength of the relationship between two variables measured on a continuous scale. This index can provide evidence that two variables are related to each other, or that they are not, but does not, in and of itself, demonstrate a causal association between two variables. In this chapter, we were also introduced to the concepts of explained or shared variance and the coefficient of determination. Determining how much variance in one variable is shared with or explained by another variable is at the core of all of the statistics that are discussed in the remaining chapters of this book. In particular, correlation coefficients are the precursors to the more sophisticated statistics involved in multiple regression. Coefficient of determination, a statistic found by squaring the Pearson correlation coefficient that reveals the percentage of variance explained in each of the two correlated variables by the other variable. Versus correlation coefficient, a statistic that reveals the strength and direction of the relationship between two variables.